Welcome back, everybody. So now we're going to see another example of a set dominating another set. We're going to show that whenever you have an infinite set A, omega, the natural numbers, are dominated by A. Okay, so what we want to do is to define a function from omega to A that is 1 to 1. Okay, and all that we know about A is that it's infinite. And remember, infinite, all that infinite means is that it's not equinumerous to any natural number, right? So that's all that we know about A. So what is the idea to define this function h? And the idea is to be defined by recursion. So we're going to say, well, we're going to define h of 0 to be some element of A, which A is not empty, so just an element. And h of 1, some other element of A, and h of 2, some other element of A, and h of 3, some other element of A. And we go like that, one by one, keep on defining. We're never going to get stuck because A is not finite, so there's always something else to choose. And like that, we're going to end up defining our one-to-one function. It's one-to-one because we always choose a new element that's different from the previous ones. Okay, so that's essentially the proof, except we have to be a little bit careful about a couple of things. So, okay, we're choosing one element because A is not empty, fine, we can choose one. But here we're choosing infinitely many elements. We're doing a recursion, we're choosing infinitely many elements. So an A could be some huge, weird sets that I don't know what its elements look like. How we're doing the choosing, who's doing the choosing. So we do need to use the axiom of choice, actually a weaker version of the axiom of choice. But the axiom of choice is going to allow us to do the choosing. So let's do that first. So we use the axiom of choice to define a function, let's call it C for choice, that takes every subset of A, well, except for the empty set, and picks an element of A such that the image of a set, let's call it B, the subset of A, belongs to B. Okay, so we are only choosing sets B that are subsets of A and B are not empty, right? So for every subset of A that is not empty, we can just choose an element of itself. We're assuming it's not empty, so we're just choosing an element of itself. If you want to say, how do we do this using the axiom of choice? So notice that a graph C is included in the set of pairs B comma B, which belong to the power set of A minus the empty set cross A, such that B belongs to B. Right, so this thing on the right, this thing up here, it's a set of pairs. On the left we have subsets of A that are not empty, and on the right we have elements of A. And this is a set of all the pairs which satisfy that B belongs to B. So this is a property, this set up here we can define by the subset axiom. And this is a relation, it contains a bunch of pairs, it's just a relation. And what we want is a function, not a relation. Well, a function is a relation, but with the particular property that everything here is assigned only one element here, that assigns to each B a unique B, right? And that's exactly what the first form of the axiom of choice says. If you go look, it says that whenever you have a relation, you can take a function whose graph is a subset of the relation, but it's choosing for each possible thing in the domain only one thing in the range. While here in this function, each capital B is related to all its elements, right? So if B has 10 elements, there's going to be 10 pairs, capital B comma something, choosing all the elements. The relation contains all of those pairs. Our choice function contains only one. It's choosing one of these little b's for each capital B. Here is our slide from a few weeks ago about the first form of the axiom of choice. Whenever you have a relation from one set to another, which one element can be mapped to many different elements, we are choosing just one of the possible elements it maps to, right? So every relation R is a function, is our choice function, which has the same domain. So all these guys are going to be related to something. This is the domain. And the graph of the function is what is a subset of this relation. But now every element is assigned only one. So this is the red line here, means from these two, we chose the red one. From these two, we chose the red one. Yeah, so that's what the axiom of choice said. Okay, so now that we have a choice function that for every subset of A picks an element from itself, from inside itself, we define H by recursion. H of 0 is going to be just, we just have to pick an element from inside A. So we're going to choose the choice function of the whole set A is going to give us an element that belongs to A. And then in general, we're going to define H of n plus 1 to be a member of what set we want. We want something that belongs to A, but it's not equal to any of the previous ones to make it one-to-one. So we're going to remove the set H0, Hn, right? And now we're going to get that this is going to be a member of A. The choice function is going to choose a member of A, and that is different from H0, Hn, right? And we have to make the observation that this set is not empty because A is not finite. And if it was if it was empty, we will have a bijection. Right, the bijection is right there. H will be a bijection, mapping 0, 1, 2, 3 up to n to A. So we will have that A is in bijection with the number n plus 1, which we know is not because it's not finite. So then we can define this function all the way through. So we end up with a function exactly like we wanted from the natural numbers into A, that is 1 to 1. Okay, so the natural numbers are dominated by any infinite set. As a corollary, we get that a set is finite if and only if it's not equinumerous to any proper subset of itself. Right, so we already show one direction, if you guys remember. So we already showed that if a set is finite, it's not equinumerous to a proper subset of itself, and that was essentially the pigeonhole principle, that you cannot map a finite set like properly inside itself. But now what this lemma gives us is the other way around. If A is infinite, we want to define a bijection, let's call it F, from A to a proper subset of A. And how are we going to do that? Well, we know already that we have our map here, let's say the natural numbers, and here is our set A. And we have our map H, so we know we have a one-to-one function from omega to A, no? That goes, whose image is somewhere inside A, maybe it's the whole thing, but it's somewhere there is the image of this function. And now what we can do is the natural numbers, we know how to map the natural numbers to a proper subset of it themselves, right? We just shift them by 1. We add 1 to every number, then 0 is going to be left out, and every other map. And we get this one-to-one function from omega to a proper subset of itself. So we can do that inside this part. So shift this one, and then that will give us a shift of this one, leaving 0. 0 is going to be left out, and then here H of 0 is going to be left out. And then we leave the rest the same. Okay? So we can do the following. For A in A, we define f of A depending on whether A belongs to the range of this function H or is outside. So if it doesn't, if it's not in the range of A, we just let it be itself. So A, if A is not in the range of H. Okay, so if A is up here or up here or up here, we let it just stay fixed. And if A is up there, then we just take the pre-image, we add 1, and then we go back. So we're going to define, we're going to let it be H of H inverse of A plus 1 if A belongs to the range of H. Remember that H is 1-to-1, so if you belong to the range, you can take the pre-image, right? So that, what we're saying here is that if you're taking an element from up here, if this is your A, we are mapping, we are going back here, taking the inverse, then adding 1, and then we go back, right? And we get something else. Yeah. So what are we getting right here? F is 1 to 1, and it goes from A to A, and it's leaving out the image of 0, right? Because the image of 0 is never h of something plus 1, because this something plus 1 is never 0. Okay, so in the infinite case, you can map to a proper subset. In the finite case, you cannot, and this is a characterization of being finite. So we could have used this one as a characterization of what it means to be finite, and then do a proof that this is being finite is equivalent to being equinumerous to the natural number. Some people do that, depends on the textbook. Okay, see you in the next video.